So let's see how Sage can help us work with the 4 fundamental subspaces of a matrix. What I've pre-written here are 4 blocks of code, and each block of code will tell us whether or not a particular vector lives in one of the 4 fundamental subspaces. So this first cell here has 2 lines of code that we need to input. The first line is just the definition of a matrix A that we're interested in, and the second is defining some vector V that we're interested in. And here what we're doing is we're trying to test whether or not a vector is in the null space of this matrix. So we have 4 print statements here. We'll print out the matrix that we input. We'll print out the vector that we input just to make sure we don't make any typos. And then we'll print out A times V. That will tell us whether or not we're in the null space. We just have to check whether or not that equals 0. And then the last line will actually interpret that equation for us. So let's click Evaluate. So here we're working with a 3 by 4 matrix that we predefined. And the vector we were dealing with is 3, -15, 15, -1. And when we multiply this matrix by this vector, it looks like we produce the vector 0, 0, 0. That tells us that this vector is in the null space of our matrix. So again, we can mess around with this. If we change this -1 in the third coordinate to a positive 1, that'll almost surely give us a new vector that's not in the null space. And here we see that's true. By changing that last coordinate from -1 to 1, now A multiplied by V is not 0, 0, 0. It's 0, -24, -6. So the answer to whether or not V is in the null space now is no. V is not in the null space. What does the second block of code do here? The second block of code will tell us whether or not a vector is in the left null space of a matrix. So remember, to be in the left null space means when we multiply by the transpose of our matrix, we produce the 0 vector. So here we have almost the exact same data, except now we multiply our vector by A transpose to verify whether or not we live in the left null space. So let's click Evaluate and see what my predefined code does here. So here we have a 3 by 4 matrix again. And what we're going to do is we're going to multiply the transpose of this matrix by a vector in R3 to produce a vector in R4. And here we see that when we multiply our matrix transposed by the vector 2, -6, 5, we produce -11, -1, 5, 57. Well, that's certainly not the 0 vector. So we know that the vector we're working with is not in the null space of the transpose, which is also called the left null space of our matrix. What does the third block of code do here? The third block of code will test whether or not a vector is in the column space of a matrix. Here we're using the Roche-Capelli theorem by checking whether or not the rank of the matrix is equal to the rank of the matrix obtained by augmenting our matrix with the vector in question. So let's see what happens. So here I've predefined a matrix and I've predefined a vector. The matrix we're working with is 3 by 4, and the vector we're studying is the vector 4, 2, 5. Well, when we row reduce that augmented matrix, what we can interpret for ourselves here what the data says. When we get the reduced form, we find that we have 3 pivots, here, here, and here. None of those pivots is in the augmented side of the matrix, so we know that this vector is in the column space of our original matrix. So the answer to whether or not V is in the column space is yes. In this last block of code, what we're doing is we're trying to verify whether or not a vector is in the row space of a matrix. So here we use almost the same syntax, except we transpose A before we do anything. So let's click Evaluate and see what the predefined code does. So here we have our matrix we predefined, and we're looking at the vector -45, -12, 17, -160. So the first print statement takes our matrix we defined, transposes it, and then augments with the vector in question. Then, in the second print statement, we print out what happens when we row reduce that augmented matrix. And here we find that we get a pivot in the augmented column. That tells us that the vector we're studying is not in the column space of the transpose, which again is called the row space of a matrix. So we can use these four blocks of code to determine whether or not a given vector is in any one of the four fundamental subspaces.